All right, so we're going to start off this little video demonstration by giving a visual of what's going on and kind of setting up our problem here. So first things first, we've got two different angles. I've kind of color coded them, hopefully to give you a good visual. But first one is the green angle. We're going to call that angle alpha. That angle rotates all the way from this horizontal axis up and over. It's an obtuse angle, and it gives us a particular measure that looks like it's bigger than 90. Okay, so that whole angle is alpha. Our second angle is the red angle. Looks like a little smaller angle just for this demonstration. That angle rotates from the horizontal up, and we're going to label that one beta. And the last thing that we want to do is what we're actually interested in is we're going to look at the angle in between these that's formed in between these two angles. So let me highlight that real quick. So I've thrown these two blue segments in here to highlight the angle in between, and we're going to call that angle. That angle is going to be found by taking the whole angle alpha and then subtracting out the smaller portion of beta. So this is the angle that we're interested in here, and it is alpha minus beta. All right, so last thing we want to do here is we want to label these these coordinates of the angle, or of these points, these endpoints here. All right, so the first one, we want to know what the x coordinate is. That x coordinate is given by that angle of rotation alpha. So the x coordinate is going to be cosine of alpha, and the y coordinate is going to be given by the sine of alpha. That's going to give that vertical component, or the y coordinate of that one. Over here, we're going to use beta as the reference angle, and very similarly, the x coordinate is just the cosine of the angle of rotation, and then the y coordinate is going to be given by the sine of that angle of rotation. So we have these coordinates. We've kind of labeled everything on here, and the next step is we're going to kind of transform this or rotate this around to give us a different view or a different visual. All right, so next thing we want to do is we're actually going to rotate this thing right here so that it comes all the way down to the x-axis, so that that ray, or that segment of this central angle, is going to sit on that horizontal component there, on that horizontal axis. And accordingly, we're going to we don't want to change the angle. We want to keep the angle the same. So we're going to rotate this angle along the circle the same amount. So let's go ahead and do that just to give you a visual of what that looks like. Here's this segment. We're going to rotate it down to right there. And this segment we're going to rotate over to about right there. Now, notice we've kept this the same. We've kept this angle the same. And so if we've kept this angle the same, that means it's still alpha minus beta, this angle. So lastly, what we want to do is we want to write the coordinates of these points now that we've rotated them around to the origin, or the original position. This point right here would be 1, 0. And then this point right here, the x coordinate would be the cosine of the angle, which is alpha minus beta. And then the y coordinate is going to be given by the sine of the angle of rotation, which is alpha minus beta. All right, so I've cleaned this diagram up a little bit, and in doing so, what we want to do is we want to now take a look at some expressions, equivalent expressions that we can write. So number one, these are both alpha minus beta, and because they're both alpha minus beta, we want to look at the distances. These distances, or the lengths of these segments, are going to be congruent. Okay, so we want to write what those lengths would be, the lengths of those segments, using the coordinates that we've labeled on here. And just big picture understanding that those two segments are going to be congruent. So whatever expressions that we come up with, these are going to be equivalent expressions. So we're going to start with this first one over here on the left. We've got our points labeled, and so if I want to find the distance for the first one here, we'll call this D1, first distance, it's going to be the square root of x2 minus x1, so that's cosine of beta minus cosine alpha, and we're going to square that, and we're going to add that to our y2, which is sine of beta, minus our y1, so that's sine alpha squared. And similarly, let's write an expression for this distance over here. We'll call this d2. Okay, so this is d2. And we know that that distance, again, is just given by x2 minus x1. So it's a square root of x2 minus x1, that quantity squared. And we're going to add that to the difference between y2 minus y1 and that quantity squared. All right, so hopefully now that we've got an understanding where this stuff came from, we can kind of hone in on the algebra. The next couple steps are going to be pretty algebra heavy, but really it just kind of centers on expanding these binomials squared, or these squared binomials, and so we're going to do that. So let's start with this one over here, this binomial squared. We're going to have first is cosine of beta times cosine of beta, so that's a cosine squared of beta. Outer and inner is going to give us two of these, cosine alpha times cosine beta. And last is going to be negative times a negative gives us a positive, and that's a positive cosine squared of alpha. So there's our first expression. Really similar expansion for the second expression, so let's go ahead and get to work on that. Second expression is going to be plus sine squared of beta for our first. Outer and inner is going to give us 2 sine alpha sine betas. And then our last is going to be a negative times a negative. That's a positive, and it's a positive sine squared alpha. So here's our big long expression for the distance. Again, that's under a square root. And just in the back of our head, keeping in mind that these two expressions, the one on the right and the one on the left, are going to be equivalent, and we'll use that later. So similarly, we're gonna expand these two things out. I'll pause the video and do that work and kind of jump ahead. I'd like to encourage you to pause the video and do the work on your own just to confirm. But here's what that looks like. All right, so the next step is kind of a grouping step. And we need to recognize one of our trig identities in here. And that trig identity is the Pythagorean identity, Pythagorean trig identity. And it says that the sine squared of any angle plus the cosine squared of any angle is going to be equal to 1. And so we're going to use this as we combine some of the stuff, some of the similar, or group some of these similar expressions. So let's go ahead and get to it. So we've got on the left side here, a sine squared of alpha and a cosine squared of alpha. So that's going to give us sine squared alpha plus cosine squared alpha. And we've also got a sine squared of beta and a cosine squared of beta. And then we've got these two expressions here, this guy and this guy, that we'll just kind of tack on the end here. So minus 2 cos alpha cos beta, and then a minus 2 sine alpha sine beta. Similarly, on the right side over here, we've got this sine squared and cosine squared. So we'll just kind of rewrite those. So I got a sine squared of some angle, and that angle happens to be the combination of 2, or the difference of 2. And I've got a cosine squared of that same angle. I've also got a 1 and a minus 2 cos of alpha minus beta. So again, we're just kind of manipulating, rearranging. These are all still under this big giant square root. And when I move forward, hopefully we can see, based on that Pythagorean trig identity, that that's just a 1 and that's just a 1. So this gives us a 1 and this gives us a 1, which gives us a 2 overall. So that's nice. It kind of cleans things up for us. And it's a 2 minus a 2 cosine alpha cosine beta minus a 2 sine alpha sine beta. Again, that's all under square root. So that simplifies things for us a little bit on the left side here. And on the right side, we've got this expression here, which is just a 1. So that's the square root of 1, and then plus another 1. So we've got a 2 minus 2 cosine of alpha minus beta. So we've cleaned things up a little bit here, and I think we could take one step farther and factor out. So I'll go ahead and do that. So we've got this thing down, simplified as far as we can go algebraically, and at this point, it's where we're going to remember that these two expressions were just expressions for equivalent lengths, and these two, distance 1 and distance 2, were actually the same thing because we just rotated this angle over. So we're going to set these equal, and when we set those equal, it allows us to manipulate both sides. So we're going to square both sides, and that cancels the square root, and then we're going to divide by 2. And it's going to get rid of that 2, and it'll leave us with this expression, 1 minus cosine of alpha cosine of beta minus sine alpha sine beta. And that's equal to 1 minus cosine of alpha minus beta. All right, so at this point, what we're trying to do is we're trying to get this expression right here by itself. Okay, so we want to move our 1's over. If I subtract 1 from both sides, it effectively just cancels those. And what I've got to do is I've got to turn this negative sign positive. So we're just going to kind of flip the signs or multiply both sides by a negative. And what that does is change each one of these signs. When I get a positive cosine of alpha cosine of beta plus sine alpha sine beta, and that's equal to cosine of alpha minus beta. And there's our formula for the difference, for the angle difference in cosine.